Is this okay? Okay. So my name is Amanda, and I'll be talking about how we can employ causal discovery to improve subgrid parameterization in our climate models. So for some background, I'll just talk a bit about what a causal graph is, and then talk about how it relates to subgrid parameterization. For a causal graph, essentially what I want to do and what you can do with observational data is you can take each variable, put it into a node, and then create like arrows between the nodes to basically explain and explore how different variables can causally relate to one another. And to give you an example, let's say you want to measure the effect of smoking on lung cancer rates, but you might have like a what you call confounder. So another variable like alcohol consumption. Alcohol is a carcinogen, and it might affect how many people get lung cancer if they consume more alcohol, but people who consume more alcohol might also smoke more. So it's hard to actually measure in an observational data set whether smoking actually contributes to lung cancer rates if we have some sort of confounder like X. And yeah, so that's the top right graph. And then for the bottom right graph, so what you want ideally is the C implies Y and then T implies Y. So there is nothing between C and T. You can replace C and T with like X and Y. So there's no arrow between those two nodes. But in observational studies, we often do have that confounder. And I want to revisit Rebecca's slide in explaining why this is helpful for, it's not in there, but I do want to reference that Rebecca mentioned how currently our climate models have like grid cells, right? But then there's sometimes an embedded subgrid parameterization because we don't have all the variables that we want. And we're going to be like kind of estimating them, hypothesizing about them. And we're using machine learning right now for that. But machine learning isn't always the best option. There's a lot of overfitting to the data set, and especially given that climate change is impacting like how hot and cold and extreme weather temperature and climate temperature can be, it's important that we have machine learning models that are a lot more robust and that rely on actual causality rather than correlation. So that's the point of my research. And yeah, so here's the methodology for how I go about discovering the causal graph from observational data. I assume a couple of things. I assume that the data is stationary, so any like variance mean stays constant over time. I assume causal sufficiency, so I list most of the confounders in the causal graph, and that there's no instantaneous effect. So there's always a lag time of 1 day in between each variable. And the PCMCI algorithm that I use to basically take the observational data and create a graph out of it is called the PCMCI. It's composed of 2 parts, so the PC1. And what the PC1 does is it first creates a skeleton graph, as you can see on the left. And then it identifies immoralities. So immoralities are what A, B, and C would be right here. Once it has immoralities discovered in the graph, then it uses these assumptions I've referenced to create a true graph. And then once you have that graph, the MCI part of the algorithm will distinguish between the indirect and direct causal links by using partial correlation and significance level testing. And this is just an example of what the output would be. You don't have to read it all, but you just input some parameters and alpha values you want, and then you get out basically a list of variables with how many links each variable has. And then these are the data points, the variables that I use. So the blue ones are my inputs, and then I'm trying to predict rain rate. So that's my output. You'll see on the right that 2 of the inputs have levels of 60 because there's 60 vertical columns. I'm only going to be taking 6 of each level. So I'm doing a step size of 10. So I would take the specific humidity at level 0, 10, 20, 30, 40, 50. And then, as I said before, I relied on a lot of assumptions to create the causal graphs. So I want to eliminate like mean deviations and seasonality. So I normalize the data and remove seasonal cycles. And these are more specifics about the climate data processing. As I said, I use a one-day time step, selected 6 levels. And for the selection process of the causal graphs, I retained the directed links with a p-value of negative of less than 0.05. And then I tested a range of significance levels in the PCMCI algorithm. And these are my results. So I have 2 slides, and these are just the most promising causal graphs that came out of came out of the algorithm. I used a tau min and tau max of also 1, so it only shows time lags of 1 on here. And I'll go through maybe what you should notice in the graph because there's a lot going on. But out precipitation is the rain rate that I'm trying to predict. And then you'll see in most of the graphs that the PBUF Solin, which is the solar insolation, often is not related, is not a parent of rain rate. While you'll see that the state PS, which is surface pressure, is often related to the rain rate. So here's this examples again for those. So as you see, yeah, PBUF Solin is never a parent, but state PS often is. And then the arrows, like the color of the arrows, just depends on like how correlated they are, with like closer to 1 or -1 being a higher positive or negative correlation, respectively. Some takeaways from those graphs that you may have noticed, like I said, is that surface pressure and surface heat flux often directly affect precipitation according to the causal graph, and that the strongest causal links can be found at certain levels of specific humidity and air temperature when combined. And then, as I mentioned, solar insolation never seems to predict precipitation. And then some next steps from creating the causal graphs would be to test it on a neural network, especially with those combinations of inputs that I identified. Ideally, I think I would try to test like maybe 60 separate neural networks, since I had around like 60 separate outputs from my PCMCI. And then I would like to also like plot the like alpha values I use for the PCMCI algorithm in comparison to the R² of the neural network. So I could see maybe at what like ideal inputs are like would be helpful to capture the missing information in the neural network. And yeah, that's it.
Again, we'll take questions from in the room, but we do have one online that we can just get started with. From Rohan Kulkarni, he asked, what seasonality did you use on the data and why?
So to answer Rohan's question, I didn't use seasonality, but I removed it from the data set. So that means that the data, even though there's a time step of a day, there isn't changes in like any of these variables by whether it's winter or summer. The data stays constant.
We have a question from Sammy.
I have a question about the assumptions that you mentioned for like doing causal inference of like sufficiency and things like that. Are there ways from a data set to assess like how the degree to which those assumptions hold, like know whether your data set is causally sufficient or not, and like based on that act differently, or is it kind of just like an assumption that's not really clear how you might know that because you don't know what other variables like exist in the world?
I think some of the package I use to get the causal graphs is called Tigermite. And I think there are some causal sufficiency like algorithms and functions that you can use within that to test between like different data. But I would say that a lot of the reason I picked these data points was because of like background research on, I didn't mention this in the presentation, but yeah, background research on like which data points I absolutely must include.
Hello, great job presenting. I was wondering, so you said you removed seasonality, and I remember you mentioned before, but I couldn't remember what you said. What is still that oscillation in your standardization? Like, is that a diurnal cycle? Is like, what is that then if you don't have seasonality?
If you want seasonality, I think it's noise. I also added some noise to the data because the research paper that I based my research this summer on also added, I think, some noise. So I just wanted to make sure I was reproducing it as accurately as possible. So it could be from that.
Yeah, I think based on your plots, the seasonality still exists there a little bit, but you kind of was able to remove most of the cyclic signals. Great work. Thank you, Amanda.